صباح الخير للجميع وربنا يعطيكم خير هذا اليوم. Let me just describe everything in English because some audience from English background, if you allow for me. And please, Dr. Light, if you can help me to share my...
Okay, I think you are now co-host. Okay, you are co-host, Professor Bitar now.
I don't know, I cannot share. Now?
I think you are already co-host. Share screen.
Okay, now it's okay.
Okay, yes.
So first of all, let me express my deep appreciation for the conference organization committee and for the chairs and co-chairs of this well-reputed conference that's hosted by Amman Arab University, which is a very good university and very well-reputed university at Jordan. Also, let me also introduce myself. I'm Dr. محمد البيطار. I'm currently the head of Artificial Intelligence Research Center at Ajman University, and I'm lead from البيطار University again. And today, inshallah, I will present my research area, which I have researched on this area for 15 years ago, which is evolutionary computation. So the evolutionary computation, we will start the talk by introducing what is the evolutionary computation. Then we will move to introduce the main concern of this evolutionary computation, which is optimization problem. Then we will describe the historical evolutionary algorithms that come at the beginning, and then we will describe the recent evolutionary algorithm. Then we will move to the contributions that can be made for the evolutionary algorithms. And finally, we will describe briefly, because we are running out of the time, I think, so we will describe briefly some applications tackled by evolutionary algorithm. The evolutionary algorithm is an artificial intelligence subfield, closely linked to the computational intelligence, and involving lots of combinatorial optimization problems and continuous optimization. The main concentration of this field is to tackle the optimization problems, which are looking for finding an optimal solution in between a big or plethora of optimal different alternative solutions in the surface space. So this concept comes from the evolutionary principles, where the human being normally start evoluting. This is based on the Darwinian theory, start in this form and until they stop in the last format, which is a complete and healthy person. Let me just also describe where is the evolutionary computation in AI, because in AI we have many different techniques that can be used for tackling the AI problems. So normally the AI problems have some input data, and we have a model, and we are looking to have an output data. So if the input data is known and the output data normally in the classification problem is known, and we are looking to have a model, this model is proper to map the input to the proper output. So this type of a problem is called modeling problem or machine learning or deep learning problem. If the input is known and the model is already known, or the algorithm is known, and the output is unknown, this is the normal algorithm solution or normal simulation problem. While for optimization, let me go further. Next slide. So in the optimization, the model is known together with the desired output, and the task is to find the input to this output. This is normally either minimization or maximization. So we are looking at the keywords of the optimization domain. So we are looking for the smallest, biggest, maximal, etc., etc. So the input is the unknown, component, and we have a very big thousands of applications, such as timetabling, schooling, nursing, and call centers. For engineering, we have a very big number also of optimization problem in engineering domain, such as design specification, economic law, data structure design, and for the computer science problems, we have also traveling salesman problem, ATPs, etc., etc. The main important thing in the optimization domain or in the evolutionary communication domain, we have a problem with a search space, and this search space reflects the ruggedness of the problem hardness. So if the search space is very huge and the number of variables that should be recognized is very huge, the search space will be rugged and considered as NP-hard. And normally the search space has two dimensions. So the vector of the variables that we are looking to find the optimal solution, and the objective function that measure the quality of each vector or each input vector. So each optimization problem should be modeled in terms of solution representation, which is X, and the evaluation function or objective function. And this is the search space, where the search space has several search space regions. Each push point is representing the solution, and the peak is the global optimal solution, either global minima or global maximum. So these variables in the vector X can be in the form of binary or discrete or continuous or real world or real values, sorry, and permutation and structural solutions. So in order to solve this optimization problem, we have to have a strong evolutionary algorithm. So the evolutionary algorithm, the idea of using technique based on the emulation of the mechanism of natural selection to solve the problem, can be traced as long back as 1930 actually. And however, it was not until 1960s, only appeared in 1960, that the three main techniques based on the notation were developed: is genetic algorithm, evolution strategy, and evolutionary program. And the founder of genetic algorithm is Holland, while the founder of evolution strategy is Schwefel, while Vogel is the founder of evolutionary program. And all of these are based on the evolutionary principle of the survival of the fittest. Okay, the main structure or schemata for any evolutionary algorithm is can be described in this format. The first thing that we have to know is that evolutionary algorithm is a population based. Means that we have to initialize a population of solutions, population of individuals or population of solutions, where these solutions are randomly or heuristically can be included. And this kind of algorithms has an iterative loops, and this iterative loop take the solutions in the population and improve this solution based on such operators. So we have selection operator called parent selection, where from the population we will select the fittest group of solutions, as many as the population size, as a parent for the next generation. And these parents, when they determine, we will generate or we will operate recombination and mutation operators to generate a new population, which is called offspring, as many as also the population size. After the offspring are generated, we will use the survivor selection, where the survivor selection is another operator that selected the fittest offspring to be the new population. And normally they use the replacement, direct replacement between the offspring and the population. So the offspring will replace the population directly. So this is the general schemata of any evolutionary algorithm. So this is the procedure code of the evolutionary algorithms. So we have initialization of the solution, and then we will evaluate them based on the objective function. Then we will move through an iterative loop, and this iterative loop will be terminated based on some termination conditions, such as the time, number of iteration, maybe when we reach the optimal solution. And at each and every iteration, the operators, these operators will be flipped. select parents, recombine pair of parents, mutate the resulting offspring, evaluate the new candidate, then we will select the individuals, and again until we find the optimal solution. So the main, as I mentioned previously, the main thing that should be utilized at the beginning when you try to tackle the optimization problem using any evolutionary algorithm, you have to do solution representation. So we have two spaces actually, the phenotype space and genotype space. In the phenotype space, this is the real representation. This is such example based on the traveling salesman problem, and everyone I think know the traveling salesman problem, where the salesman will travel to visit all the cities once. So this kind of representation, which is the real representation called phenotype space, it will be moved to the genotype space, where the solution, each solution will be represented in specific formats such as binary or discrete or continuous. Also, for the parent selection, how we can select the parents from the population, we can use different selection mechanisms such as proportional selection, linear rank, exponential rank, tournament selection, global based, and random selection. And for example, proportional selection will assign, this is a kind of proportional selection, will assign for each solution a selection probability. This selection probability is assigned to each solution based on its fitness value. So if the solution has a high fitness value, it has a higher chance to be selected to be a parent for the next generation. So this is proportional selection. Linear rank is based on the on the ranking of the solution. And all of this is a type and kinds of selection mechanisms. And this is the initial selection mechanism. Nowadays, we have a plethora of selection mechanism used in the new optimization and evolutionary algorithms. For the recombination, and this is also a general term, the simplest form of the recombination is the crossover, where we have two parents and we will mix their attributes together to generate new offsprings of two children. So this is how we can use one-point crossover to mix the properties of the two solutions to come up with new offsprings. The mutation is the operator that's responsible for diversity or diversify the solution to go through different search space regions in the problem search space. So sometimes it's not guided by any objective function or not guided with any criteria. So it's easily, if we use flip-flop, we can select randomly in a specific rate. And normally the mutation rate is very low, one gene from the chromosome or the solution, and just a flip-flop. For the survivor selection, where after we generate the new offspring, and after the crossover and the mutation, maybe we need to select the solutions or the offspring to be the new population. Normally, we do the replacement, direct replacement, but sometimes maybe we can mix the parent solution and we can mix the offspring solutions, and we can do elitism, where the best portion of the upcoming solutions will be selected, or we can use generators where we delete the worst, or we can use round robin tournaments or lambda selection or plus lambda selection. For example, plus lambda selection, we will combine both the parent solutions with offspring solution, and we will order them based on their fitness function, and then we will select the highest fitness functions elements, as many as the population size. The fourth versions, oldest versions and traditional versions of evolutionary algorithm are genetic algorithm, evolutionary strategy, evolutionary programming, and genetic programming. And those are different from each other based on the component that they use. For example, genetic algorithm used for binary search space, and they use one-point crossover or two-point crossover. The mutation normally is petit flip. The parent selection is a fitness proportional with the roulette wheel selection, and the survivor selection is generational replacement, where the whole where the whole offspring will replace the population. In the evolutionary programming, it is used for real valued vectors, and there is no recombination, and the mutation is Gaussian mutation, and the parent selection is deterministic. So based on the difference of the evolutionary algorithm components, the new algorithms will come to the fore. So this is another versions of evolutionary algorithm, which is called evolution strategies, which is deal with a problem with real valid vectors and discrete. The recombination or crossover is discrete or intermediary, where the mutation is Gaussian mutation, and the parent selection depends on the random selection, not utilize any survival of the fittest principle, and the survivor selection is mu, lambda or mu plus lambda. For the genetic programming, which is rarely in the research domain is used for the problem with the tree structure or graph structure. And the recombination is exchange of subtree, and the mutation is random change in the tree, and parent selection is the fitness proportional, and survival selection is the generational replacement. The next generation of the evolutionary algorithm, which is established in 1996, actually, it is the differential evolution and the swarm intelligence. And the first swarm intelligence introduces particle swarm optimization. And also, I here defined the main component of evolutionary algorithm for differential evaluation, such as in the differential evaluation, it is designed to deal with real valid vectors or continuous domain, and the recombination is uniform crossover. The mutation is differential mutation. The parent selection is uniform random selection of 3 necessary vectors, and the survivor selection is deterministic elitism replacement. In the particle swarm optimization, actually, or in the swarm intelligence, in the most cases, there is no recombination, and they are established to deal with real valid vector. And the mutation here is adding a velocity vector to the original vector or to the original solution. And the parent selection is deterministic, where each parent create one offspring using the mutation operator. And the survivor selection is direct replacement between the parent and the offspring. Nowadays, the domain is redefined, and the evolutionary algorithm became meta-heuristic based algorithm. And we have we have more than hundreds of evolutionary algorithms and optimization algorithms or meta-heuristic algorithms. And I here categorize them to different families, such as evolutionary algorithms. We have just a few here. Local search algorithm, swarm intelligence algorithm. We have an algorithm that established from the physical phenomena, the algorithm that established based on the chemical phenomena, and algorithms that established based on the human phenomena, such as harmony search algorithm and coronavirus herd immunity optimizer. Actually, the next thing that I want to discuss here, how can we contribute to improve the performance of this evolutionary algorithm? Normally, the performance of this evolutionary algorithm is tightly depend on the search space of the problem that should be tackled. And most of the real world optimization problems are very rigid and very hard to solve. And they have a very huge search space with a very huge alternatives, and finding the optimal solution with this type of search space is very hard, and we need to adjust the operators of the evolutionary algorithm. The original version cannot be work for many optimization problems. So we can adjust these algorithms based on the diversity control mechanism, the parameter tuning, the multi-objective constraint handling, and mimetic algorithms. So I will describe briefly each one. For the diversity control mechanism in evolutionary algorithm, we have mainly 2 approaches: implicit approach and explicit approach. The implicit approach is concerning with the geographical separation of the population. So we have two main mechanisms, which is Iceland model and cellular automata. So here the population will be divided into several subpopulations, and each subpopulation will be run as a separate evolutionary algorithm. And after specific number of generation, the exchange process will be happening. When the solar automata, the population or the solutions will be arranged as a grid, and this grid has different shapes, and this topology, for example, can be used as a subpopulation. So this is the main solution in the red button. So the yellow is the neighboring solution, and this neighboring solution can be considered as the population to be generated. In the implicit approaches, we have a very famous two approaches in the implicit approaches that also focus on the diversity, which is fitness sharing and crowding. In the fitness sharing, we will redefine the objective functions of each solution to have the distance between the solution and its neighboring solution. So we will divide the solutions to neighboring to different groups, and based on their sharing fitness value. In the parameter tuning, normally the parameters of the optimization or evolutionary algorithm has an impact on the performance. So we have to have a proper values for these parameters at the beginning of the search to guarantee an optimal solution that you published. So here, a very famous research in 1999 by Ippen established and distinguished the work or research done for the parameter tuning of evolutionary algorithm to the parameter setting to parameter tuning, where the values for each parameter of the evolutionary algorithm should be set before the run of the algorithm, and we have different strategy here. And we have another way which is called parameter control, where the parameters will be undergoes changes during the search or during the run process. So we have here three possible ways: deterministic, adaptive, and self-adaptive. In the deterministic, we will consider the iteration number to define or to recalculate the value of the parameter, while in adaptive we will take in consideration the fitness function value, while in the self-adaptive we will use another method to configure the parameter for the current method. In the multi-objective research domain, here we have some problems in the optimization domain has more than one objective function. So this is called multi-objective. So it maybe have 2, 3, or 4 objectives. And here we have not only one search space, we have search space for the solutions, and we have search space for the objective function called objective space. So each solution here is evaluated against not only one objective function, maybe 2 or 3, and this is a vector. Here in this example, only with 2 objective functions. So each solution has a vector of 2. And let me describe the two approaches, the main two approaches that is used for multi-objective optimization. The first one is weighted sum, where we can combine and integrate all of the objectives in one objective function, and we will provide a weight based on the preference to each objective function, and we will calculate one value. And so in this way, we will convert the multi-objective to single objective optimization. And the second way, where the majority of the research done, is in the Pareto optimality. The Pareto optimality actually is considered the objective space, and the objective space where the result of this algorithms is not only providing one solution, it's to provide a Pareto optimal set of solutions to be given to the decision makers to select the best one of them. So here, let me just describe very quickly the characteristics of each type, the single, and the difference between the single objective optimization and multi-objective optimization. The number of objective is 1, here is more than 1. The space is single, while here is the decision and objective space. The comparison here is because we have only one objective function, so we can just say if the objective function value of the solution X is better than Y, we will consider something, or maybe replacement will be occurred. But here we have to consider this comparison way, where we will ask if X dominates Y. X is a vector of solution, and it has a vector of objective function. So, and the X dominates Y, this means that all the objective function should be the same, as well as we have at least one objective function better than the existing objective function of the x, so of the y, so we will consider x dominate y. Okay, the resulting solution again here is the optimal solution, while here is the set of solution called Pareto optimal solution. The algorithm goal is to converge to the optimal solution, while here to converge and to diversify the solution, so we need a diverse solution at the end of the search. The constraint handling, as I mentioned, the most real-world optimization problem has several constraints, and it has to be solved under a set of constraints. So we have to adjust the evolutionary algorithm to deal or to handle these constraints. And we have normally two types of methods to handle these constraints. We have indirect and direct method. In the indirect method, we can add the constraints satisfaction rules to the objective functions, and we will try to manage this constraint as an objective function part, while in the direct method we cannot move until we solve this constraint satisfaction. So we will, if any constraint is violated, we can do repair for this constraint violation, or we can do restart mechanism, and we have different also mechanism here and different research done in this place. For mimetic algorithm or mimetic evolutionary algorithm, also it is another branch of research that's also heavily tackled. Also here we can make use of the strength of the local search mechanisms to improve the diversity and local exploitation of the evolutionary algorithm. So here in the optimization loop or in the evolution loop, we will add a local search to navigate the search space of the problem more tightly or more seriously. There are thousands of problems of optimization problems tackled by evolutionary algorithm. Here I mentioned very few, which is traveling salesman, bin packing, trust optimization, quadratic assignment, max, SAT, and many other optimization problems. And nowadays, optimization problems are connected with the machine learning and deep learning algorithm to find the optimal hyperparameter for the evolutionary, for the machine learning and for the deep learning method.